Like the hands that pull the strings at a marionette puppet show, our resident microbes influence the day-to-day running of virtually all of our biological systems. For instance, host-microbe interactions during the first 3 years of life are particularly important for the development of the immune system, and perturbances to the gut microbiota, or dysbiosis, during this critical time in early life can have long-lasting detrimental effects on health. Until very recently, this microbe-mediated immune education was thought to be initiated when a newborn baby leaves the relatively sterile environment of the uterus and is seeded with its mother's microbes, but work from our group and others in the last few years has shown that the maternal microbiome. Bonnie HOFKIN in the mid-2010s, when we started our work on the role of the maternal microbiome during pregnancy, there was no direct evidence that mom's resident bacteria affected the developing baby. However, it seemed naive to think that the influence of the maternal microbiota would start only at birth. We knew that maternal antibodies crossed the placenta to protect the fetus from infection, and we suspected these antibodies could also direct the maturation of the immune system. We also knew that commensal bacteria, in addition to pathogenic microbes, trigger the development of antibodies. Moreover, we thought that perhaps microbial products or metabolites could also be transferred to initiate exposure to a microbial world even before the baby is colonized with his or her own microbiome at birth. Now, just 5 years later, we know this to be the case. Both bacteria-produced molecules and maternally derived antibodies appear to drive immune development in utero. Many unanswered questions remain, and we are far from understanding the long-term significance of this phenomenon. However, it seems increasingly possible that our mother's microbiomes may, to some extent, shape our health and well-being before we are born. Developmental origins of health and disease during delivery. Babies are exposed to the maternal microbiota. Children born by the vaginal route are colonized by vaginal and fecal microbes, while those born by Caesarean section are instead predominantly seeded by the maternal skin microbiota and sometimes hospital-acquired microbes. The importance of this vertical microbial transfer is apparent in the higher rates of immune, metabolic, and neurodevelopmental disorders among babies born by C-section. After birth, it takes several years for a child's microbiota to fully develop and diversify. This is a dynamic process, heavily influenced by external factors including hygiene, antibiotic usage, and diet, including human oligosaccharides from the mother's milk. In the same time frame, the offspring's immune system is undergoing intense development and maturation and is highly susceptible to microbial imprinting. Exposing young children to antibiotics during this critical window has been associated with an increased susceptibility to several diseases, likely due to the indirect effects that these drugs have on immune development. In 2013 and 2014, as researchers began to question the role of the maternal microbiota during pregnancy, several groups launched epidemiological and animal studies to examine whether in utero antibiotic exposure poses a similar risk to a child's health. This was first demonstrated in 2015, when Yujia Hu and colleagues from Yale University showed that prenatal antibiotic exposure influenced the development of type 1 diabetes in the offspring. Since then, a number of other studies have similarly demonstrated effects on offspring of manipulating the microbiota of pregnant mice, either with antibiotics or dietary intervention. Researchers have observed such results in a variety of models, with implications not only for diabetes, but for susceptibility to asthma, obesity, and colitis, as well as the progression of autism-like behaviors. In most circumstances, manipulating the maternal microbiota changes which microbial communities are passed from mother to offspring at birth, and subsequently alters immune development in the neonatal host. It has therefore proven challenging to attribute the immune phenotypes described in most of these studies to the maternal microbiota directly, as opposed to those mediated by the newly seeded microbiota of the neonate. Fortunately, we are beginning to tease these differences apart, and tantalizing hints are emerging that the maternal microbiota educates the immune and nervous systems of gestating offspring remotely. See, the infant gut microbiome and probiotics that work. Bonnie HOFKIN. Maternal microbiota shapes infant antibody repertoire. For decades, we have known that antibodies are passed from parent to fetus during pregnancy. They play a huge role in protecting babies from infection both before and after birth. However, we are only now beginning to appreciate the role the maternal microbiota plays in shaping the antibody repertoire. We are also gaining new insights into other roles for antibodies beyond binding to pathogens and protecting from infections. By adulthood, the intestine is home to the body's largest collection of immune cells. As it is continuously exposed to enormous amounts of foreign antigens, derived from both the microbiota and our diet, the intestinal immune system must learn to tolerate innocuous food components and symbiotic microbes while retaining the ability to mount a successful defense against harmful pathogens. Moreover, all microbes can quickly become harmful if they enter the bloodstream, even those that are considered symbiotic when living in the gut. Antibodies such as immunoglobulin A, IgA, secreted by B cells at the mucosal surface lining the intestines, are transported across the gut epithelium into the lumen, where they bind to microbes and prevent them from passing through the intestinal epithelial barrier. The immune system of a newborn infant is inexperienced. The fetus is not thought to be colonized with its own bona fide microbial communities. Traditionally, researchers thought that maternal antibodies transferred across the placenta were specific to infectious microbes that might infect the baby while its own immune system was still developing. This transfer of antibodies might partly explain why newborn babies fed breast milk are less susceptible to developing necrotizing enterocolitis, NEC, a severe and often fatal inflammation of the colon that can occur when babies are born prematurely. The reason that preterm babies are highly susceptible to NEC is unclear, but it is widely postulated to be a consequence of their immature immune systems overreacting to the abrupt colonization of their GI tracts, something that full-term babies typically handle without issue. These and other results imply that immune education in the final weeks before birth is important for babies' immune systems to tolerate friendly bacteria. As well as functioning in the GI tract, commensal targeting antibodies from breast milk can be actively transported across the epithelial barrier of a baby's intestine and into its circulation, ultimately disseminating throughout the body. At least a portion of these anticommensal antibodies can cross-react with pathogens. While it is unclear whether the transfer of antibodies across the placenta in utero contributed to protection in this model, it seems likely that they acted in concert with antibodies transported via breast milk to protect the neonate. The many effects of microbes on offspring during pregnancy. The body is subject to numerous changes. The composition of the gut microbiome shifts, metabolism changes, and the gut epithelium becomes more permeable. After birth, maternally derived antibodies help newborns tolerate the bacterial colonization of their own GI tracts, while simultaneously protecting them from enteric and systemic infections. The antibody-mediated transfer of metabolites increases antimicrobial peptide production, which strengthens the epithelial barrier to prepare the gut for microbial colonization. The permeability of intestinal epithelium increases during pregnancy, facilitating interactions between the microbiota and a mother's immune system. If microbes that escape the intestinal lumen are not immediately ushered back in, antibodies from mom tag them for efficient elimination to limit inflammation. At Studio Lindaloo, Linda Lubberson. Older pups. As the pups age, the immune education that they received in utero and shortly after birth protects the animals from inappropriate inflammatory reactions that can lead to allergy, metabolic syndrome, or other health consequences. See full infographic. Web PDF. Microbial metabolites also influence infant immunity. The maternal microbiota is not a one-trick pony. It does more to shape the offspring's immune system than induce the production of antibodies that are shared with the newborn. By breaking down the food we eat, and molecules secreted by other resident microbes, intestinal microbes produce a wealth of metabolites with wide-ranging immune modulatory functions. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.